Okay, we're now recording, and let me check if you can see my desktop sharing. Just 1 second.
I have no light over here.
Can you see me drawing?
Yes.
All right. Let me just check the boundaries. This is the left corner of the drawing, top left. This is top right. That's the bottom right, and that's bottom left.
Right there.
Good. Okay, let's start with assignment with the problem 1, and I'm going to switch real quick to the assignment. And this way. Okay, for some reason I cannot find this window for my sharing. Maybe it's not standard. Just give me 1 more second. But you should have the text of the assignment handy, so I will just go ahead. The first problem is to convert numbers in one number system to another. And there are a number of tricky questions that I prepared for you. So you not only consider a number system as something trivial, as binary or octal or hexadecimal, but from the perspective that a number system can be pretty much anything. So, say, in the example, actually, in the assignment, I'm asking you to come up with a number system of base 23 as an example of number system with base 1 and 5/3. So what, for example, would be a number system, a number system with base 23? With base 1 and 5/3. So what, for example, number system of a number? Let me mute you, Rob, because I can hear some echo. All right. So a number system with base 23 will have to have 23 unique symbols to represent numbers in this number system. By analogy to a decimal number system, where we have 10 being a base of this number system, we have to allocate 10 unique symbols. And we just used to think of a decimal number system as having 0, 1, 2, 3 all the way to 9 as the digits representing parts of a number. But those 0, 1, 2, 3 all the way to 9 are nothing more but just unique characters that we use. And to extend the idea of a decimal number system, we're talking about hexadecimal number system, that after 9 we have a letter of A, followed by B, C, D, E, F. So in other words, 10 different digits plus 6 different letters give us 16 different characters to represent digits of a number in hexadecimal number system. And hexadecimal number system is a number system with base 16. That's why we have 16 digits. So a number system in base 23 will just have to have 23 unique digits, or 23 unique characters to represent the digits, better to say. And you can just extend the idea of hexadecimal. Say you start from 10 possible digits from 0 to 9, and then to represent 11, or to actually represent 10, there will be A. To represent 11, there will be B. To represent 15, there will be F. To represent 16, there will be G, and so on and so forth. I cannot say right now what will be the a digit for 22, but I can tell you ahead of time that there will be nothing to represent number 23, or actually digits 23, because number system with base 23 will have unique characters to represent from 0 to 22, but never 23. And it seems a bit strange, but if you think of this as just an extension to a number system similar to what we have with decimal, say we start counting from 0, 1, 2, 3 all the way to 9, and what follows the 9? We create another digit, the second digit in the higher order place. That's why we come with the 10. 10 is nothing more but 1 times base of a number system, which is 10 plus 0. And let me do some drawing in this regard. Okay, where is my... Say with I know 5 with base 10. We have just one single digit called 5, and since it is base of 10, we never go beyond 10. That's why it's going to be 10 raised to the power of 0, because this is digit with index 0 times 5, and pretty much obviously it is 5 because 10 raised to the power of 0 is just 1. But we can extend this example and say what will be 15 in base 10. 15 in base 10 will be 1 times 10 raised to the power of 1 plus 5 times 10 to the power of 0. So 1 and 5, those are digits of the original number 15. And those powers of 10 are written in decreasing order. So 10 raised to the power of 1 is to represent this one. So you can say this is going to be power of 1, this is going to be power of 0. If we have 3-digit notation, for example, 749, 749 will be 7 times 10 to the power of 2, because power of 2 is associated with this digit, power of 1, power of 0, plus 4 times 10 to the power of 1, plus 9 times 10 to the power of 0. In this case, we're talking about 700 plus 40 plus 9. But it is decimal number system. If we go to extend this idea and let us say consider hexadecimal number system, then by analogy we can say 5 in hexadecimal number system will be 16 times 16 raised to the power of 0 times 5, and obviously it is 5. What will be 15 in hexadecimal number system? It will be 1 times 16 raised to the power of 1 plus 5 times 16 raised to the power of 0. And now the tricky part is how to convert this notation into something else that we can deal with. We natively operate with decimal number system rather than hexadecimal number system. And this notation is already written in a decimal number system, because think of this number 16. It uses decimal notation. We just used to think of numbers represented in decimal number system. So I would say that everything to the right of this border is nothing more but our own view to a hexadecimal notation, but expressed in decimal notation. And in this regard, it will be 1 times 16 will be 16, plus 5 times 16 raised to the power of 0, which is 1, plus 5 to get 21. And this 21 will be in decimal notation. So 15 in hexadecimal, it's 21 in decimal. And if we just continue with other number systems, say, let's consider 15 in a base number system with base 20. By analogy, you can say it is 1 times 20 raised to the power of 1 plus 5 times 20 to the power of 0. And this is obvious. We're not going to continue. But how, for example, we would write a number that contains digits that are greater than 9? So I can say, for example, that f, or I think some glitch has happened. So f3 raised to the power of 20, or I'm sorry, f3 in decimal in number system with base 20, what will it be? It will be f times 20 raised to the power of 1 plus 3 times 20 raised to the power of 0. So what is f times 20 raised to the power of 1? It is f times 20. But what is f? And then we start counting. We say that 9 is 9, and then a is 10, b is 11, and then all the way there will be e, which is 14, and f, which is 15. So f is 15. In other words, it's going to be 15 times 20 plus 3. 15 times 20 is 300 plus 3, so it will be 300 in base 10. This is what kind of calculation you want to be able to do. And pretty much the same we can say about a number in, about a number in number system with base 23. There is no difference in terms of operation. So, but with 23 we have 10 digits and then 13 letters. What would be 13 letters? So if f is 15, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, 16, 17, 18, 19, 20, 21, 22. Okay, we have to stop at 22 because there cannot be a digit to represent 23. Same as we don't have a digit to represent number 10 in decimal number system. Instead, we have 2 digits, 1 and 0. Same here, m will be the highest character to represent a single digit in a number system with base 23. So in other words, to construct a number in a number system with base 23, we have to operate either with digits from 0 to 9 or with letters from 1 to m, or from A to m. And this constitutes a number in number system with base 23. So for example, I can say a good number would be J37 K59. So this could be a number in base 23. And if you want to convert it into decimal, you could say, since it is 0, 1, 2, 3, 4, and 5, it will be j times 23 raised to the power of 5 plus 3 raised to the power 23 raised to the power of 4 plus and so on and so forth. But what is j? J is 19. So 19 times 23 raised to the power of 5 plus 3, 23 raised to the power of 4 plus. And then there will be some number in base 10. That's how you proceed. Any questions? Okay. Now, the tricky part about number system with base 1. If we want to consider this number system following the same assumption, we probably want to recall the fact that a number system with base 2 give us digits 0 and 1. A number system with base 3 would give us digits 0, 1, and 2. So what will be a number system with base 1? What kind of digits will we have in this case? By extending this idea, there will be the only digit, 0. So in other words, a number system with base 1 is not a fully functional number system, but if we try to use the same theoretical approach to represent numbers of base 1 number system, then we can say that the only possible digit would be 0. And actually, since 0 is the only type of digit or type of character that represents digits of such number system, you can combine them at any order. So for example, you can say a good example of a base 1 number system would be this, or would be this, or 4 zeros, or any other number of zeros. As long as your characters are zeros, you're okay with base 1. But if one of those characters, for example, becomes non-zero, so this is not a valid representation of a number system with base 1. Okay. Talking about fractional bases, like 5/3 in the assignment. I'm not going to give you an example right now because this is probably the greatest challenge of the assignment. And more you can find in problem 3, which is specifically dedicated to fractional number systems. And particularly problem 3 asks you to convert number 173 from decimal to 11/3. 173 from decimal. This is problem 3. 173 from decimal to something in base 11/3. One thing about fractional number systems or number systems with fractional base is that the base has to be greater than 1. So 11/3 is a number that is greater than 1, and you're good to go. 5/3, it's a number greater than 1, and you're good to go. But you cannot represent, for example, number 25 in decimal number system in something else written in number system 3/5, because think of this: 3/5 is a number that is less than 1. With base 1, we already had a deficiency, but we're talking here about something less than 1. So deficiency will be will be present in even more scale. So that's the rule of thumb that you have to remember. Your digits, your base number system of a fractional base has to be greater than 1, like 5/3 or 11/3. And following the algorithms that you can find by looking at the links that I posted on the assignment statement in problem 3. There is actually a research article that discusses fractional number systems, and I want you to look through this research article. So pretty much from this research article you will find out that if we're dealing with a base number system, with a number system with base, for example, 11/3, we really have to care about the first number to give us a span of digits for this number system. So 11/3 contains 11 as the numerator, and this 11 dictates how many distinct digits there will be in the representation of a number system with base 11/3. The fractional part, actually denominator, also affects the way how the number system will be expressed. But you may think of this 3 is something related to the following fact. So what is 1/3 in decimal notation? It would be 3.66 and 6 in period. So it is a number greater than 3 and less than 4. Okay? So if you, for example, asked, as in the assignment in problem 3, to convert number 173 from decimal to something with base 11/3, this is for you to predict the length of the result. So if it was just a base 3, then you would have certain numbers from 0 to 2, and the magnitude of a number in terms of how many digits there will be, what will be the form of expansion, and then the 4 will give you the other boundary. So you will have something in between, and then later on, when you will have the result written, it will be comprised from those digits from 0 to b, and then I don't know the result, but it will be something like 2, 3, 8, 7, 2, 1, I don't know, 5. And the way how you proceed, you would need to raise 2 times 10, I'm sorry, not 10, 11/3 raised to the power of 0, 1, 2, 3, 4, 5, 6, plus 3 11/3 raised to the power of 5, plus and so on and so forth, plus 5 times 11/3 raised to the power of 0. Because it is nothing more but just yet another notation of a case of a number system. From this perspective, you can say, okay, 11/3 raised to the power of 6 likely will have something in numerator, something will have something in denominator. And if we add everything up, it's not going to be an integer, but we are looking for this notation to be resolved into an integer 173 in base 10. The tricky part is that you have to multiply it by something here to make it integer. So the research article that I'm pointing to discusses how to derive those digits, but the process will be pretty much alike to what you have to use in problem 1. And then we'll tell you what kind of multiplier has to be used here in order to make sure that such an expansion of this number actually results in 173 in base 10. So I would suggest you to start from reading this article, and then following this reading, you should be able to easily operate with number systems of fractional basis. But again, make sure that this base is greater than 1. Otherwise, you wouldn't be able to convert from here to here. Okay? Any questions? You can just, okay.
Real quick. My internet browser will not let me open that article that you linked to on the PDF.
You probably can.
You think I should just try a different browser, or it says there's like a security issue with it?
No, it shouldn't be security because it's in public domain. I opened it right before posting it, so let me just double check. Okay, I have just opened it, and there could be an issue with extra forward slash. We try to. Okay, I posted on the chat section. Can you open it from there?
Let me check real quick. Let me see.
The chat session is on your right.
On the right. Hold up. There it is. Okay. Okay, yeah, it opens up from there. That's
Okay.
good. All right.
There was an extra forward slash in the link caused by the fact that the link was going on one line of the text to another. That's why there were 2 forward slashes in one place. But after I removed it, it should work for you.
All right, yeah, that's good. Thank you.
Okay, anything else?
I don't think so.
That will be, you definitely will face a number of difficulties, but as I said earlier, the earlier you will discover those difficulties, the more prepared you will come to our tutorial sessions. So instead of me to predict your problems, you will come with problems ahead of time, so we can work with these problems. But since it is more, the first assignment is more like an illustration of the concepts that you already covered in assembly language course, it's pretty much not that directly related to the topics of computer organization. It's just a refreshment. So try to treat this as just tricky version of assembly language. That's what I would say. Okay, let me go ahead with other problems. And problem number 2, again, it's conversion from decimal number system to other number systems. And one thing that you always have to remember, that if result in some other number system shows digits which are greater than a base, for example, the first subproblem of problem 2 is to convert to base 7. Base 7 doesn't allow a digit to be greater than 6. So in other words, we're only allowed to use digits from 0 to 6. If at any part of your conversion you will have a digit in your result which is greater than 6, it means you're doing something correctly. Just have this in mind. Okay, and let's move on to problem number 4. Problem number 4 discusses ranges and precision. Ranges and precisions are very important concepts in digital, I would say, digital world. It's probably not seen that much in your everyday life, but computers deal with this in pretty much all the time. The general idea is, so for example, what will it make for you in terms of an effort to multiply number pi, which is 3 and many more digits? What if we want to multiply it by something like 0.73999? This is just an example. So we have learned the procedure to do such type of multiplication, and we just temporarily forget where the decimal place is located, the decimal point is located, and we just multiply the two integers of a large scale. So for example, let us say everything to the right of this border in number pi is not defined, so we just want to multiply this big number, which is 415,926 multiplied by 7,399, and then we will probably properly place a decimal point just to make sure that number of digits to the right of this decimal point matches the total number of digits from this area and from this area. This is how we have learned to multiply fractional numbers, I would say. But computer is more or less optimized piece of equipment, and instead of counting how many digits are there, it actually tries to first represent a number. Because if you think of this problem as a problem of infinite precision, you probably can recall that those digits that are not listed in number pi, they do exist. The only thing that we can ignore them at some point, but they do exist. This is, for example, what will happen if we divide 10 by 3. We can just say that it is roughly 3. If we need more precision, we can say it is roughly 3.3 or 3.33 or even more number of 3's. This is called 3 and 3 in the period. But what number will be stored in the computer? And it looks like to actually represent this number in computer memory, we have infinite number of digits in this representation. Infinite number of digits will eat all the memory. But does it really make sense for us to store all these 3's in the memory? Because since there are infinite number of digits of this kind, we're obviously going to consume all the computer's memory. So instead of doing this, we're trying to deal with numbers of this kind from a different perspective. Instead of saving this, we just save number 10 and number 3, and that's it. And then, for example, if we want to multiply this original number by 2, instead of doing 3.3333 multiplied by 2 to get another infinitely long number, which is 66666, we're going to deal with another number to be represented as 23rd. So that is the concept that is implemented in computer, and this is called fixed point operations. Actually, it's not a fixed point operation, but this is basis for the fixed point operations. The real concept called fixed point operations is that we do not allow infinite number of digits being stored in the computer memory if we want to represent a number. In other words, what we do, we ignore a precision in favor of easiness of operating with such a number. So, for example, if we know that our application doesn't really care about everything that is to the right of this border, why do we need to store all this infinite number of 6's? And the reason for us to make this conclusion that we don't need anything to the right of this border would be to say if I use this number in the context of adding up to 1000, does it really make sense to add 1000 plus 666 and bunch of other sixes, or just to say to add 1000 and only few sixes? So probably we can just ignore the rest portion of number 6.666 and just concentrate on the first part. In this case, we can just say we don't need anything to the right of some border. In other words, from now on, we deal with numbers that have two parts. The first part that represent an integer portion and another part that represent the fractional portion. Since we disregarded the rest of the digits, we're going to lose. We're going to lose not the big fight where we use this number in the context of arithmetical operations, but we're going to lose the fight with precision, because those numbers will never be stored in the memory, they will be gone. If we want to somehow recover the precision, there is no way out. We just truncated this number, these digits, and that's it. From now on, we just think of a number 6.6 in the period as 6 and 3 sixes. This is our way to think about this. And now this number only approximately equal to original one, but we save the space. We save the space in the memory. And how much space do we save? Let us say every digit in decimal notation can be anything from 0 to 9. Let us just say preliminary that we deal with decimal notation. From 0 to 9. If we make it very rough, we can just say every digit is a single byte. Of course, it is not a single byte, because with 1 byte of information, we can represent 256 different characters. But with the decimal notation, we have only 10 different characters. So instead of allowing 256 different characters, we're just talking about 10 distinct characters to represent decimal number system. But let us just say roughly in the memory, this number will be represented by 4 bytes. Since we fixed the amount of memory allocated to store this number, we introduced a standard. From now on, if we want to operate with numbers of that kind, we just want to represent every number in a 4-byte memory cell. And limitation of the 4-byte memory cell dictates what kind of operations we can do. Because, okay, let me clean it up. So now we're dealing with any number to be stored in 4 bytes. And I just mentioned this, that 4 bytes for us are 4 different placeholders, 4 different digits. If it is a decimal point located here, then what will be the highest number that we can represent? Probably will be number 9, and then all 9s. What will be this number? It will be very close to 10. But in fact, it is 9.99939. What will be the minimal number in this representation? It will be 0.001. So the minimal number in this representation dictates the precision. And precision is the terminology that you can see in the assignment statement. So precision is the minimal difference of 2 neighboring numbers. And that's exactly true in this context, because how close 2 different numbers in such a notation? What will be the neighbor, the closest neighbor to this number? It will be 1 with 8 in the last position. And difference between these two numbers, like 9, 9, 9, 8, will be this. So this is called precision. This one is called the maximum, the range, in other words. So we're talking about range, we're talking about precision. And range actually is, if you look at the assignment, we're asking about minimum and maximum number. I'm asking you about minimum and maximum numbers which can be presented, and the precision, the smallest non-zero representable number. It looks like minimum and the smallest non-zero representable number, they are the same. And that's pretty much correct, because with very little error we can say that since this is our precision, we still can represent 0 as the minimal number. So 0, 0, 0, 0 will be in fact, okay, not this one, will be in fact the minimal number. So to clear up everything that I've said, these two numbers will form the range. This number will form the precision. But as of now, we've used the decimal notation. In the assignment statement, you are asked to use binary notation, but you just need to extend this idea. In binary notation, we don't deal with numbers of form from 0 to 9. You deal only with digits 0 or 1. And for example, if instead of 8 digits as given in the assignment, you ask to deal with 8-bit fixed point binary number, let us say we have to deal with 4-bit binary number. 4-bit binary number, let us say we place a binary point in between the two. So 2 bits to represent the integer part, 2 bits to represent the fractional part. What will be maximum value in this case? Maximum value will be all ones here and all ones here. Okay. What will be the minimal value? We know that it's going to be 0, 0, 0, 0. What will be the precision? 0, 0, 0, 0, 0, 1. That will be the precision. Okay. But now we want to think about how this representation from the binary perspective can be converted into decimal. We know that if it was no decimal point, then integer part represented by 2 binary ones is equal to 3. Right? 2 binary ones gives us 3 in decimal notation. And the way, why do we know this? Because it's going to be 2 raised to the power of 1 times 1. I addressed the first one. Plus 2 raised to the power of 0 times that second one. Okay? If we want to continue, we have to go beyond the decimal point, this decimal point. So we want to continue decreasing the power of 2. So it will be that one, but multiply 2 raised to the power of negative 1. And plus 2 raised to the power of negative 2 multiplied by another 1, which is this one. So now you just want to add up everything together. The first part to the left of this line gives us number 3. Okay, 2 plus 1. But this part introduces the fractional portion of a number. 2 raised to the power of negative 1, it is 1/2. 2 raised to the power of negative 2, it is 1/4. 1/2 plus 1/4 is 0.75. So 375 is a representation of the maximum number in this binary notation. Okay? 0 will be 0 even in decimal number system. What about precision? We just use exact same mechanism for expansion. It will be 0 times 2 raised to the power of 1 plus 0 times 2 raised to the power of 0. So our integer part will be 0 plus 0 raised to the power of 2 to the power of negative 1. So 0 times 1/2 plus 1 times 2 to the power of negative 2, which is 1/4. So in other words, precision would be 0. Sorry, let me just write here. 25. 1/4 times that 1. So this will be precision. This will be maximum. And this will be minimum. 0.0. And by analogy, you just want to do the same with the problem number 4, but with the 8 digits where the decimal point is located to separate the 5 digits to the left and 3 digits to the right. So instead of 2 and 2, you will have 5 and 3, but the mechanism is the same. The application, the greatest application of the fixed point arithmetics is actually to speed up computing. Nowadays, it's probably not that important because our CPUs in desktop and laptop computers and in cell phones, in smartphone devices are very powerful, and they do have hardware support of floating point arithmetics. So there is no need to compute, to deal with fractional point numbers in this regard. But if you think about embedded electronics, something that you can see installed in your microwave, or something that you can see installed, I don't know, in your DVD or Blu-ray DVD player, there you can find processors that also have to deal with data processing, and they deal only with specific type of data, and those types of devices, they have to be very fast, they have to be very efficient, and hopefully they have to be not that much expensive. Because the fractional point processor that you can see installed in any modern computer, it's actually expensive part, expensive add-on to the main CPU functionality. You will talk about this floating point processing in the context of computer architecture course in coming fall if you're getting registered. But floating point, it's a separate type of operations. You're also going to lose some precision, but much less than what we do here. So in other words, we use fixed point arithmetics if we know that range of numbers is going to be certain. For example, when we use bb.bb, we know that the highest value will be 375. Precision, precision will be 0.25, and the minimum value will be 0. Okay, but what if we need to represent a number that is greater than 3.75? What do you think we need to do? We can just say that instead of placing a decimal point here with the same amount of memory, we can just say we want to place the decimal point here, one position to the right. In this case, our maximum value will be 725, minimum will be 0, precision will be 0.25. No, 7.5, I'm sorry. And precision will be 0.5. So now we can deal with a higher value using exact same amount of memory as before. So in other words, it is a trend. We have to decide whether or not precision is more important, because previously our precision was 0.25. Now our precision is 0.5. We don't have this good precision, but the range of numbers is now greater, twice greater than before. If we actually can completely disregard precision operations, we can just say that, okay, let us just place the decimal point at the very right position. So the maximum range will be 15 to 0, and then precision will be just 1, because 1 will be a difference between two neighboring numbers. Okay, but in this case we have no way to represent the two. But the beauty of this approach is that since for every number we still use 4 bits, we actually can multiply this number by this number, say 1101. I'm going to multiply by 0101, and that was the point. And the same rule of arithmetics will take place. We just want to multiply the two binary numbers, which will be 1011, all zeros, and then 1011 to get the result 100001. Doesn't matter what will be the result, I just don't have a space to write. And then we want to place a decimal point to actually respect this decimal point. And then it depends how much space we use for the result. If we say that our result is the same 4 bits, then obviously the result of multiplication doesn't fit the 4 bits. But usually when we deal with multiplication operation, we have to reserve the additive number of bits that were in operands. So in other words, 4 bits was with operand A, 4 bits with operand B. To store the result, we have to have 8 bits. That's just a rule of thumb, and that's the rule that is respected in any digital design. So in other words, all digits will be there, and the decimal point will be just located one position to the left from the least significant bit. That's how you get the result. And the good thing in this approach is that it is understandable to a human being. It is very fast because we don't need to deal with fractional point numbers like a number pi with thousands of digits to the right of the decimal point. We deal with fixed number of digits. Yes, we lose precision, but the speed of operations is very great. That's the greatest advantage of fixed point arithmetics. Any questions? No? Good. And to practice with arithmetics in different number system, there is a problem number 5. And let me just give you an example to these problems. Say you're asked to convert first argument to the number system of the second argument, and then present the result in decimal number system. So let us say I have 3 in base 7, and I want to add it up to, I don't know, 15 written in, I don't know, base 3 number system. Okay, let us just say I want to calculate this. First of all, can you see any problem in this notation? Let me help you.
Different bases.
This number is incorrect because I cannot represent number 15 where one of the digits is 5 in a number system with base 3, because base 3 allows me to use only 0, 1, and 2. So in other words, this is incorrect. It cannot be 5. It cannot be anything in the range from 0, 1, and 2. So be careful. There are a number of problems that show this type of challenge. So let me say instead of 15, there will be 12 in base 3 number system. Okay, so first of all, I have to convert 3, 7 into something base 3. Okay, how would I do this? Of course, if you're comfortable to do direct conversion, you can do this. But if I was you, I would convert 3/7 to decimal first, because decimal number system is more native for our human being operations, and then from decimal to the third. So let me first convert 3 base 7 to something base 10. And we already know this, that it's going to be 7 raised to the power of 0 times 3, which is what? Which is 3 in decimal. So 3 base 7 is 3 base 10. Okay? And now we want to convert 3 base 10 into something base 3. How this conversion will work? To convert from decimal to something else, I have to divide by the bases. So in other words, I have to divide 3 by the basis, which was 3. Okay, and I just write 1, 3, remainder will be 0. Okay, since result of the division is already less than the base, I have to stop. And my result is going to be combined from digits. The first one will be the quotient, and then the rest will be all remainders along the way. We have only single remainder, which is 0. So in other words, here I want to write 1, 0 of base 3. 10. 3 base 10 is 10 base 3. Right? So 3 base 7, it is 3 base 10, it is 10 base 3. And now we want to add 10 base 3 to 12 base 3. And the way you do it, just respect the same operations, the same approach as you would do in a decimal number system. Okay, so we have to add 12 in base 3 number system plus 10 in base 3 number system. I don't use the 3 here, I just remember that it's going to be base 3 operation. So in what way base 3 operations are different than base 10 operations in terms of addition, subtraction, multiplication, etc., etc.? The only big difference is that any digit cannot be greater than 3. Same as in decimal number system, any digit cannot be greater than 9. Any digit here cannot be greater than 2. So let us just start. 2 plus 0 gives us 2. 2 is not greater than 0, so we're going to leave it as it is. And then 1 plus 1 would give us another 2. So that is the result. 3 base 7, it is 22 base 3. And now the problem asks us to convert the result back to decimal. So 22 base 3, we want to convert to something base 10. and this is pretty obvious. We want to 2 times 3 base 1 plus 2 times 3 base power 0. So this will be 2 times 3, which is 6, plus 2. So it is 8 base 10. So result of that operation, 3 base 7 plus 12 base 3 expressed in decimal number system, is number 8. If you want me to demonstrate addition which is a bit more tricky than just 12 plus 10, okay, let me do this, but before I went ahead, let me know if this is clear. Okay, so if this is clear, let me do just some abstract addition of two numbers that are not that obvious. For example, I want to add 59 of base 11 plus 17 of base 11. Okay, first of all, the check. 5 is not greater or equal than 11. 9 is not greater or equal than 11. That's okay. Same with the 17. 1 and 7, they are less than the base. So these numbers are correct. Let me now add 7 plus 9. We know that in decimal number system it would be 16. What is 16 in decimal if we convert it to something in base 11? What will it be? To convert from decimal to arbitrary base, we have to divide the number by the base. So 16 has to be divided by 11. It will be 1, 11, 5. So that 1 is already less than the base. So we have to stop our division. And the result will be 1, 5 base 11. So 16 base 10 is 15 base 11. All right. So now 9 plus 7 technically gives us 16 base 10, but is 15 base 11. So I write down 5, the smallest digits from this 15. And I have to carry this 1 to the next placeholder. My next placeholders is a result of addition 5 plus 1 plus that extra 1. So plus 5 plus 1 gives us 7. Number 7 is less than base 11, so I can keep it as it is. It's in other words, it's a single digit number. So this is 7511. If you need to multiply numbers in arbitrary number system, you do pretty much the same. So 23 base 5, let us multiply it by, I don't know, 42 base 5. Okay, 2 times 3. 2 times 3 is decimal 6. 6 decimal. What will be in base 5? Actually, it will be 11. So it will be 11 base 5. The quick test, 1 times 5 plus 1 times 1, it's 6. So 11, and I just write down 1 in here, and I want to carry another 1 to the next placeholder. So now I want to multiply 2 times 2, which gives me 4, and I have to 1 from the previous carry, gives me 5. I cannot use 5 because 5 decimal is no longer a single digit number. It is 10 in 5, in base 5. So it will be 0, 1. So in other words, 23 base 5 multiplied by 2 base 5 will be 101 base 5. Now I want to multiply 4 base 5 times 23 base 5. I start from multiplying 4 by 3. 4 by 3 gives me 12 in decimal, right? What will be in base 5? In base 5, I have to divide 12 by 5. It will be 2, 10, 2. It will be 22 base 5. 2 and 2. We always start from the quotient here, and then we use all the remainders. Okay, so 4 times 3 gives me 2, which is these 2, and then 2 will be carried out. So 4 times 2, it's going to be 8 in decimal. Okay. So to work with the rest here, I need to multiply 4 by 2 and add that 2. So in other words, it will be 4 base 5 times 2 base 5 plus 2 base 5. Okay, this is the number that I'm going to write down here. 4 base 5 times 2 base 5. Again, we either can do the native multiplication or through the decimal notation. Let us do through the decimal notation. It will be 8 in decimal or probably 13 in base 5. Okay? 1 times 5 plus 3 times 1 is 8. So this is 13 base 5. And then to add 2 base 5, the result will be, technically it will be 15 base 5, which is impossible to operate with. So we can just extend this same approach. So 13 plus 2. Instead of 5, I'm going to use 10, because 5 in decimal is 10 in 5. And then there will be 1 carry, so it's going to be 20 in base 5. So this is 20 base 5. 20. And actually it makes sense. When we multiply 2 by 23, we got 101. When we multiply 4 by 23, we have to have something that is twice greater, 202 base 5. And now we want to add these two together. It will be 1, 2, 1, 2 base 5. So this is the result of multiplication of these two numbers in base 5 number system. Just have this practice in mind, that if you cannot natively multiply or add up two numbers in native number system, bring them back to decimal, do the operation in decimal, and then convert them back to native number system. Anything of this gives you any question? No? Good.
Hold on. First, what did you do? Are you dividing 12 by 2 on the bottom corner on the right? In the earlier step.
Are you talking about when he divided 12 by 5?
12 by... Is it on this or...
Oh, yeah, okay, never mind.
Yeah, 12 by 5, that's for me to translate 12 in decimal to something in base 5. Like this. 12 from decimal, I divide by the base of number system to get 22 in base 5.
Okay, thank you.
All right. And the last thing about the gray code, the last question, it's actually you given numbers in decimal notation, you want to convert them into gray code. You can read about gray code in many different places, and even on Wikipedia they have nice article about this. But let me just say this: gray code is alternative to binary encoding in the following way. For example, in binary, let us say we fixed with the 4-bit binary. We can just say the 4 bits in binary would be this. These are the sequences that you might need to remember. So there is a pattern that I follow to write these numbers. And this is how you can represent numbers from 0 all the way to 16, actually to 15. So this is number 7, this is number 8, and you can just keep on counting. So this is, oh, my drone is bad. So this is the binary notation. Okay, what is wrong with the binary notation? The biggest concern in the binary notation is that you cannot use it to implement a digital device right away. For example, a digital device called counter. This is something that you will be practicing in the third assignment. It's pretty much a device that transits from one state to another. In other words, there are 4 cells in the memory, and every cell is storing a single bit. So we have 4-bit notation, we have 4 cells of the memory. Every cell in the memory stores 1 single bit. And let us say we want this memory to continuously represent numbers 0, then 1, then 2, then 3, all the way to 15, and from 15 it goes back to 0. Okay, so at first it has all zeros, next it has 0, 0, 1, then it has 0, 0, 1, 0, and so on and so forth. Here we don't have any problem, because to translate from this state to this state, we just need to change a single bit, which is the least significant bit to be changed. All remaining 3 bits are the same. Okay, but the problem first time is seen here when we convert, when we translate from number 1 to number 2. Why it is the problem? It is the problem because we want to change from 0, 0, 1 to 0, 0, 1, 0. In other words, we have to change 2 binary bits. So the least significant bit and the next one. Why it is the problem? It's because you cannot you are about to change them simultaneously, but you cannot guarantee simultaneous change because it's going to be two separate bits of data, two separate memory storages. You have no power to make this one to change from 0 to 1 and this one to change from 1 to 0 at the same time. It's likely going to be a change that either the least significant will go first, followed by this bit, or the other way around. And let us just see what will happen. If, for example, least significant bit with 0 index starts first, then from 0001 we're going to change to 0000. So we change the least significant bit. And then we want to change the next bit, which will be 0010. So eventually, result is correct. From 0001, we changed to 0010. But there was an intermediate state. And we know that this intermediate state, it did exist for a very short time, but it did exist. So instead of counting from 1 to 2, we counted from 1 to 0 to 2. And it is just extra state. It is extra information in the memory. It is something that should not be there. It is excessive data. It is a noise that we have to remove. If we assume, for example, that not the least significant bit changes first, but the next one, or bit with the index 1, then we can say from 0001, the first transition will be from 00 to 11. So this bit gets changed. And then to change the least significant bit, 0010. Again, the final result is correct. But we just have introduced a state that should not be there. Instead of 0, it is state 3. And if you look at the binary encoding, you will see this type of problem appearing over and over again. But for example, if you look at this translation, you have to change 3 bits. The least significant bit, the next one, and the next one. 3 bits at the same time. In other words, you will have more than one extra state. If you look at, for example, here, from 7 to 8, you have to change 4 bits at the same time. So many additional states will be introduced because you cannot make the change to be simultaneous. And this is where gray code becomes handy. In gray code, your encoding always changes a single bit when you convert from one state to another. So, for example, it would go this, and the next state would be this. The next state would be this. Okay? And then we want to change to this, and then 1, 1. Okay. Okay, if I'm not mistaken, no, that's going to be 0. Right, and 1, 1, and then 1, 1, 0, 1, 1, 1, 0, 0. So if you look at any pair of neighbors, you always can see just a single bit change. So this is just different type of encoding, but again, we still do it from 0, 1, 2, 3, 4, 5, 6, 7. If you want to continue with all the way to 16, you can do it. And the way how gray code is written, you want to repeat what you already have. For example, when I started from just the first two, or say I started with, yeah, with the first two. I had all zeros, the 3 zeros fixed, and now I add up one extra one in this position, and I just mirror the previous state below this line. So I changed those zeros to ones, and this is nothing more but a reflection around this line. So if I want to continue with, for example, 8, 9, 10, 11, 12, 13, 14, 15. So I want to replace all these zeros to ones ahead of time. And now I want to make a reflection around this boundary. So it will be 1, 0, 0. I repeat the previous one. 1, 0, 0 is the same here. And then I repeat this one, 1, 0, 1. And then this one, 1, 1, 1. And then 1, 1, 0. 1, 0. And so on and so forth. But you can continue right away. The problem is that it's probably not that convenient to do this every time. For example, if you need to know what will be a gray code representation of number 27, you would need to draw all this representation, and it's very inconvenient, especially if we're talking about some algorithmic solution. But what we can do instead, we can find a trend that is going to be seen. And the trend here is pretty much straightforward. Let me show you this trend on the following example. Say, let us consider the first 8 numbers in binary notation. Let me try to write it very carefully. 1, 2, 3, 4, 5, 6, 7. In binary notation, it will just require 3 binary bits. And now in gray code notation, wait, that will be 0. Will be this. And let us try to see how, for example, 3 can be converted from the binary notation to the gray code notation. And the rule of thumb here is that we always repeat the most significant digit, binary digit. So in other words, if you look at the most significant binary digit in the binary notation, binary gray. In the binary notation, they are exactly the same in both notations. So you always start from repeating the most significant bit. So for example, for the number 3, it will be 0. Okay? And then you either want to repeat or inverse the following bits. And the rule that works here is that if my previous bit was 0, I repeat the next bit. So my previous bit was 0, I repeat this one. Okay? So I do not invert it. And now to deal with this one, my previous bit wasn't 0, it is 1. I have to invert it. So that's why in gray code, one 011 becomes 010. And it can be seen on anywhere in this table, and if you continue, you will see it as well. For example, for number 6, it is from 110. We're going to translate to gray code. We start from 1 always. What do we do with this 1? It is preceded by 1, so it has to be inverted. This 1 was preceded by 1, so it has to be inverted. This 0 was preceded by 1. It has to be inverted. So that's how 110 becomes 101. So to answer the problem number 6, you're given with numbers in decimal notation, like 17. Translate it first into binary notation, and then into the gray code. That's how you get the result. And translation from binary to gray is here. You start from repeating the most significant bit, and then you either copy or invert the bits depending on what was to the left of this in the binary notation. So, for example, 10110110. That was the binary notation. What would be in gray code? We start from 1 because it was 1. And then 0, but it was preceded by 1. So it has to be inverted. That 1 was not preceded by 1. So it has to be repeated. This 1 was preceded by 1. It has to be inverted. This 0 was preceded by 1. Has to be inverted. 1 should not be inverted. This 1 should be inverted. This 0 should be inverted. Okay? That's how you convert. Any questions? Good? All right, we've covered all the problems. Now I hope you will be able to proceed.
Thank you.
Right? I'm going to pause the a thread to schedule the next assignment, but if I'm not mistaken, due date for this one, I actually don't remember, but it will be in a couple of days, right?
Yeah, the 7th. It'll be Tuesday.
7th. So in the mid-range of the next assignment time frame, there will be A2 tutorial and then the A3 tutorial. So keep looking at the discussion board with my postings and make sure that you can attend those. But they will be recorded same as this one.
All right.
All right?
Quick question.
Yes.
You said this was recording?
Yeah, it is recorded.
Okay. Someone was talking to me about that earlier. So I'm gonna...
The way how you can access this, the link that I posted on the news will bring you to the event page, and from there you will have a link to YouTube where this session will appear probably in a couple hours.
Okay, got it.
It will be on the YouTube, but you first have to follow the link that was originally posted on the news item.
All right. Just thank you.
Mm-hmm.
Pass
All right.
that information along.
Good.
Yeah, I think we're all right.
Right. In case you have any issues, there is a dedicated discussion board, so you can post your questions there. I will try to answer them.
All right.
All right.
Say bye.
See you later.